In problems 97 and 98, we want to look at vertical motion, and we're given the position function s of t is negative 16t squared plus v sub 0 t plus s sub 0, and we're working in feet instead of in meters in this particular case. So in 97, we're told that a silver dollar is dropped from the top of a building that is 1,362 feet tall. Now you have to learn how to decode special words in here. Dropped doesn't mean it was thrown down, so there was no velocity, there was no initial velocity, or that the initial velocity was 0. Second of all, we know that the initial height was 1362. You need to understand that v sub 0 is the initial velocity. The velocity at time equals 0, and in this case v sub 0 is 0. Second of all, s sub 0, which is the initial height, is 1362 feet. And obviously these values, s of 0 and v of 0, will change given for different problems. So when we put our height function together, or we can call it position function, it's the position above the ground, or the height. So s of t is equal to negative 16t squared. Then because v sub 0 is 0, the middle term goes out, and we'll simply have plus 1,362. And that is our specific position function for this problem. The first thing we want to do is to determine the position and velocity functions for the coin. So we have the position function. Remember, velocity is just the rate of change of position. So that is just the derivative of position. And so I'll write v of t is s prime of t. And we just want the derivative, sorry I missed the 2 in the 1362 above. We have negative 16t squared. When I bring down the 2, I'm going to get negative 32t. Then the derivative of 1362 is 0. And that's going to be our velocity function for this particular application. B, determine the average velocity on the interval from 1 to 2. Remember, the average velocity is just the slope of the line connecting the 2 points on the position curve. And so if you're trying to find the average velocity from 1 to 2, you need the position at time 2 minus the position at time 1. That gives you the total change in position. Then you're going to divide that by the time elapsed, and you will be able to find the average rate of change of position over that period of time. And the time elapsed from 2 to 1 is really just 1 second. So all we need to do now, you can see that you have a change in y over a change in x, or a change in position over a change in time here. So it's a slope. Now s of 2 is simply going to be negative 16 times 2 squared plus 1362. S of 1 is going to be negative 16 times 1 squared, and we need to subtract this whole quantity. So negative 16 times 1 squared plus 1362. And hopefully you can see that those 1362s, the initial height doesn't really matter. It's more a question of how much the position has changed. So negative 16 times 4 is negative 64 plus 1362. Then we have plus 16 minus 1362. So the 1362s will be a 0 pair. And we simply end up with negative 48. And that's feet per second. And I corrected the meters per second above also. So that's for B. For part C, we want to find the time required for the coin to reach the ground. And there we're simply going to take our position function and set it equal to 0. Because when the height is 0, then the object has reached the ground. So when we divide both sides by 16, we get t squared is 85.125, and the square root of that would be t equals 9.226. So that's the time when it hits the ground. And to find the velocity at that point, we simply plug 9.226 into the v of t, and that's negative 32 times 9.226, and the value is recorded there.